Assalamualaikum and hello respective panels. My name is Nurliyana Binti Hamdan and my metric number is 1986. As I bring my project to a close, special gratitude for allowing me to be here today in hope for a clearer understanding in the development of semi-active vibration control system for viscous dampers applicable in structures and buildings. Excessive vibration that come from wind, earthquake, or any transient input is something that we do not want in our structure. When the structure is induced by vibrations, part of the dynamic energy will be converted into heat energy through damping by two sources. One is inherent damping and another one is supplemental damping. And this supplemental damping is referred to additional damping that we are added into the structure through structural control devices. Viscous dampers are the most common control devices to be used in structural vibration. It functions to dissipate energy and protect against structural damage. Its application can be seen in building as a frame resistance and base isolators, while in bridges as a cable or depth vibration protection mechanism. The daily movement of traffic traveling along the bridge induces vertical vibration that could jeopardize the structural integrity, especially in reducing the bridge service life. In traditional or conventional bridges, elastomeric bearing pads are used in between the deck to accommodate the vibration. However, this current usage of elastomeric bearing pads are the most common problem in Malaysia bridges, where it is subjected to shearing or rolling, or in Malaysia it is the most commonly called walking bearing. As structural control devices can be divided into three main components, which is passive, active, and semi-active. The effectiveness of passive systems are still limited to respond favorably under different types of excitation and wideband load. Thus, this research aims in developing a semi-active vibration control system for viscous dampers applicable in bridge structure that are subjected to traffic-induced vibrations. And this could be achieved by three objectives. Firstly, is to evaluate the bridge dynamic response subjected to moving vehicle loading using a 3D finite element simulation. Secondly, is to assess the effect of implementing the structural vibration semi-active control systems on the dynamic response. And thirdly, is to perform a parametric study on the controllable damping parameter such as the damping coefficient and stiffness. The research has been conducted with regards to the flow chart as per details. Firstly, numerical modeling is developed in consideration of geometrical and material properties. Next, structure control systems are added into the structure by spring damper element. Thirdly, analyses are carried out using a transient analysis to obtain the time-dependent response. And lastly, parametric analyses are conducted on the mechanical properties of the control device. One of the bridges located in Port Klang was modeled with appropriate geometrical data received by Malaysian Public Works of Departments. A total of 5 span bridge structures supported by capped concrete column L each joint was used throughout the study. The present invention by University Putra Malaysia called multipurpose viscous damper was used in numerical study to simulate the structure control devices that are retrofitted in the bridge structure. The control measures are imposed by modifying the mechanical properties of the control unit, and in these cases, the orifice controller valve will provide an initial adjustable damping during low to moderate vibrations, and 4 different valve percentages obtained by modifying the valve position will be used in the parametric analysis. This multipurpose structure damper was best installed under the main span of the bridge deck with approximate length of 3.5 meter attached at 45-degree angle. Moving on to results and discussion, for uncontrolled response, the analysis were performed without viscous damper as a retrofitting device. Nodal vertical displacement in each span shows that the maximum displacement of bridge deck took place at 3.72 seconds, where vehicles is currently passing through the mid-span. And this cumulative displacement may lead to the damage of the bridge component, especially in the expansion joint. The response behavior under 2 different damper units shows that magnitude of displacement decreases when the structure is equipped with viscous damper. The initial displacement reduces up to 54.3% and 84.1% with 2 and 4 damper units respectively. And this shows that increasing number of damper provide additional energy dissipation mechanism capacity that will prevent unseating of the bridge deck. For highway bridges under vehicular input, there will be a significant influence on the response of internal forces acted on its pure foundation. The implementation of viscous damper was effective in reducing the internal force of the pier structure. Graph shown in the slide indicates that as the damper unit increased, the vertical force at the bottom of the pier gradually decreased. This is because part of the forces acted on the structure have been absorbed by the capacity of the viscous dampers to transform the dissipated energy into the damping force. A parametric analysis was evaluated to study the effect of damping coefficient and stiffness to reduce the peak mid-span displacement. As shown in the table, the peak mid-span displacement decreased slightly with the increase in damping coefficient and stiffness. At fully closed orifice valve position, where it is 100%, where damping coefficient is 0, and at high stiffness, the minimum displacement can be observed. As multipurpose viscous damper serve to behave as damper or as restrainer, At this state, the device will shift its behavior to restrainer, which function to connect the separated segment and unifies the induced displacement. The forces at pier supporting the midspan also reduce slightly as damper coefficient increase. However, at fully closed valve position 100% at zero damping force, the reaction force increase slightly, and these increasing force are resulted due to the state of the device which behave as restrainer. So there is no damping capacity acted on the structure, so no force are transmitted into the damping force. Under the traffic load, the movement of the structure pushes and pulls the pistons, and the damping effect can be seen due to the reciprocating motions of the piston. From the graph, high forces at 60 kN can be correlated with high displacement of the device up to plus minus 10 mm. The area inside the loop is often represent the dissipated energy in one loading and unloading cycle, and it can be outlined that the increasing damper coefficient will increase the damping force, thus increase the energy dissipation capacity. At 75% closed valve position, the device will work under the greatest energy dissipation capacity, and this will provide a better performance of the multiple purpose damper. Throughout the study, several conclusions can be made. A reduction of the deck displacement and pure forces of the structure shows that the presence of fluid viscous damper can substantially enhance the performance of the structure. This is because the damper system can reduce the bridge displacement up to 80% and pure forces up to 20%. The parametric study shows that increase in damping coefficient and stiffness can reduce the response of key indices. And the proposed hysteresis loop model shows that the energy dissipation increase gradually with the increase in damper coefficient. By that, I end my presentation for today. Thank you for lending me your ears and have a pleasant day.